Hi, welcome to Building 220 at the Johnson Space Center, where we're here in front of the Deep Space Habitat, where we've got a new analog mission going on this week, the Autonomous Mission Operations Test. We're here talking with Jeremy Frank, who is the principal investigator for the test, actually here from Ames Research Center in California. So can you tell us a little bit about what Autonomous Mission Operations means?
So, Autonomous Mission Operations is a project designed to figure out for deep space missions where the crew is going to be very, very far away from the control center. There will be a large time delay between the crew and the vehicle. For example, at Mars, the amount of time that it takes for a communication to get sent from the spacecraft back to Earth could be as much as 24 minutes one way.
24 minutes?
24 minutes.
Wow.
So, we've never operated a space mission with people on board a spacecraft at a distance like that before. So everybody understands that you can't operate a mission the same way that you do today, but we don't exactly know why not. So the Autonomous Mission Operations Project's purpose is to start to understand how it would be like to operate a spacecraft very far away from Earth.
So explain a little bit what you mean. You say we know we can't do it like we've been doing it, but we're not sure why not. Why can't you just kind of on paper say, okay, here's how we're going to do it? Why do you need an analog test to do that?
So let's pick two things that mission operations does today that might be done very differently in the future. So one of them is planning. So planning means things like figuring out what the crew is going to do on any particular day. It might mean deciding when a spacecraft is actually going to perform a maneuver. It might mean operating a piece of equipment, which means that you need to configure the power systems differently. So planning might actually be done similarly today, because typically you get a plan for an entire day or perhaps an entire week. So the process of generating a plan, sending that plan to the crew, getting the crew up to speed on that plan, that's not something that looks very different whether your spacecraft is at the moon or at Mars. But other things that the ground does quite a lot today is actually send commands to individual pieces of equipment. So if you rely on commanding a piece of equipment and getting insight into whether that commander worked or didn't work very quickly, that sort of thing probably can't be done very effectively all the way to Mars. The Jet Propulsion Lab, for example, operates the rovers and spacecraft around Mars by sending them a whole day's plan and letting it run. We can't do that with individual pieces of equipment on board spacecraft where you need insight into what happened immediately. So two very different facets of operations which might be very, very different at different time delays.
Okay. So then you test that here on the ground before we're even anywhere close to getting ready to actually go. Why is that?
So part of the reason for that is that tests that are done with very, very simple-minded simulations aren't going to have the complexity of a real spacecraft. They're not even going to have the complexity of a real flight control team. So doing it with a pretend spacecraft like the Deep Space Habitat here is a really good way of experimenting with something that approaches the complexity of a real spacecraft. And even this is not as complex as we really need to be testing with before we get to the point where we know how to build and operate an honest-to-God space mission.
So this is just kind of a first step.
This is a first step, exactly.
So how are the tests actually working? What does this first step look like?
So the way the first step works is we have a crew of 4 people who are inside our deep space habitat. We then have a flight control team that consists of 8 actual flight controllers. Each of those flight controllers is responsible for one facet of mission operations. So you'd have a flight director and a capsule communicator or a Capcom the same way that you would today. In addition to that, you would have a couple of people managing different systems. You'd have a person responsible for building the crew's plan. And what we then do is we simulate about 2 hours of activity. We simulate 2 hours of activity that's a little bit like what you would see on, for example, the International Space Station. What we then do is we run a repeated set of tests. In each test, we vary the amount of time between the flight control room and the spacecraft. We also vary what happens during the mission. Sometimes nothing will happen. Everything will go normally, there won't be any problems, the crew will basically execute their day, and you're finished. Sometimes we'll simulate a failure. We will, for example, say that part of the power system decides not to function properly anymore. Or, for example, that if water transfer activity between 2 water tanks doesn't go the way it's expected to go. and then the crew will have to decide how to handle that. The flight control team will have to decide how to handle that. Or, last and not least, we may have a medical emergency. And so you can imagine how interesting a medical emergency can be if you're very, very far away from the nearest doctor. So all of those things combined will basically tell us something about how missions would run if we ran them the way that they were run today at these different time delays. So that's the first phase of what it is that we're going to do.
And that's what we're doing this week.
And that's what's happening this week.
Okay.
Right.
And then now in June, we've got another week of testing planned, and that'll be a little bit different.
That's exactly right. So the difference between the test that we run in May and the test that we run in June is this time in June, we'll give the crews a little bit more authority, a little bit more responsibility than they usually have. And what we want to do is give them and the flight control team some different tools. So for example, today the crews don't usually plan and schedule their own day. They're given a plan that they execute, but they don't actually manipulate that plan. So what if they had a tool that helped them figure out how to actually build their plan so that if things don't go well, they can decide how to reschedule or replan their own activities.
Okay.
So that's one example of the kinds of tools that we intend to give crew in order to help them do this job differently.
All right.
But what we will do is run exactly the same set of tests, only with these tools,
Okay.
in order to see whether it makes things better or worse.
Okay. And so for doing this, you've got a crew, like you said, a couple hours at a time, working in the deep space habitat as though they were in space.
That's right.
Tell me about your crew. Who does that?
So we have 4 different crews. Each crew is led by an astronaut, and the other 3 members of the crew are mission operations director and flight controllers. So part of the reason that we did that is to make sure that each crew got the widest range of experience possible. So each crew will experience one of the time delays, each of the time delays, and in addition, each crew will experience one of the each of the situations: the normal situation, a systems failure situation, and a medical situation.
Okay. And so that gives you kind of a range of data to start looking at and then planning how we would actually do this when we do go further out into space.
That's the idea.